Alright, this is the projectile lecture. So in the projectile lecture, we are going to talk about the different types of projectiles and what classifies an object as a projectile. So, projectiles are any object that are flying through the air, acting only under the presence of gravity. So that's the only force that's pulling down on it. So we have a couple different types. So the first type is when you have an object going from a height to the ground. So there are two different ways for this to happen. It can go up at an angle and hit the ground, like so, or it can get shot straight off and then fall down to the ground. So these are our two different options for a height to ground. Now, what's important about a height to ground is not officially that it ends up on the ground, but that it ends at a position that is lower than where it started. So that's the key to that. So a height to ground projectile has a couple different, I guess, dominant traits that are very different from other types of projectiles. So, first thing is that when you have a height to ground projectile, especially if it's launched at an angle, you have a ton of variables. So it's really important that you keep these things straight. So we have delta y, cliff to peak. Delta y, cliff. Delta y, peak to ground. So we have a lot of different things going on here. So when you have these three variables, what do they look like? So your object is launched, it's going to go up, and then it's going to go down. Okay, so your delta y, cliff, is going to be from here down. That's the easy one, delta y cliff, because that's basically just whatever height it initially starts from. Then you have your delta y cliff to peak. And that is going to be from the height of the cliff to the height of the very tip top. So that is your delta y cliff to peak. Right, sorry for the terrible handwriting. Okay, delta y cliff to peak. Then you have a delta y peak to ground, which is going to go from your highest point, which is all the way at the top, to your lowest point. And that is your delta y peak to ground. So you have three different heights. You have just the height of the cliff, cliff to peak, and then peak to ground. To be quite honest, the height of just the cliff does not really do much for you. The only reason why it's important is because it directly relates to how high above the ground your projectile is. Okay, so in terms of other diagramming important piece of information, you have officially two intervals of motion here, and that's how we like to consider different physics topics, is the intervals of motion. So when we look at the motion of this projectile, it spends part of its time going up and part of its time going down. So when it's going up, that means it's got a couple different key points, and ultimately the biggest thing is that right here at this point, you are at the highest point. And being at the highest point means that you are no longer increasing your height, which means that you do not have a velocity in the vertical direction anymore. It's all gone. So you have a y velocity at the peak of 0. Okay? Now that's a good and a bad thing. The good thing about that is that when you are ending your period of moving up, that means that you have a final velocity of 0. The bad thing is, a lot of you will take that as the v final of the entire problem is 0, and that is not true. So when we're doing this, what we want to do is just pretend that this is the only thing that exists. And when that happens, that means we have a y velocity up here of 0. We're going to have an initial velocity in the beginning in the y direction of a certain size that's pointing up, and we're going to have some in the x direction that's pointing sideways. So that's how it gets all the way over to that point, because it's got to move sideways. All right, in this period of time, we're going to have a time that it takes to get from your initial to your final position, and we're going to have, as already mentioned, our delta y, and this is going to be delta y cliff to peak. So what does this all mean? Okay, essentially, what we want to do, as mentioned, is to totally forget that the other half of the projectile even exists, and to work with this like this is all we know. So, if you know the initial y velocity, which can be found using this helpful formula, v initial y is v initial total multiplied by the sine of theta. It's great. Usually you'll be given the v initial and you'll be given the angle, so this makes it very easy. All right, now you know v initial y. You know that in the y direction, the only thing that's causing it to accelerate is wonderful gravity. So that means, in terms of a formula, you already know v initial all the time, and you know g, which is an acceleration. So you know that too. So when you look at your kinematic equations, there are a couple. We have v final y is equal to v initial y plus gravity times time. We have v final squared in the y direction is equal to v initial in the y direction squared plus 2 times gravity times delta y. And that's all I'm going to worry about right now. No, I'll give you the other one. Delta y is equal to v initial y times time plus 1/2 gt squared. Now the beauty of these things is you can add all sorts of subscripts to all this stuff to make it specifically what it is that you're looking for. So if we use this equation, just worrying about what we know right now, we know that v final in the y direction, it's going to be the velocity as it reaches the peak, which we already said is 0. We know gravity. We know v initial in the y direction. So we can use this to find the time it takes to get from the cliff to the peak, which we refer to as time up. So we can use this to find time up, no matter the situation. Okay. Now, if we wanted to figure out how high above the cliff we were, you have two choices. You can either use this second equation, which totally does not require you to use your time whatsoever, which is a good thing, because let's say you, like a lot of you do on tests, which is totally acceptable, but you have to remember not to do this. A lot of you have been using v initial for v initial y as just your straight up total v initial, which means you get an incorrect value for time up. If you use time up to calculate delta y, that means you are absolutely going to get delta y wrong. So using this equation, the second one, that does not have time in it, means since you already know v final y is 0, that goes away. V initial y is over there. Now 2 times gravity, and you're looking for delta y, and that's going to be cliff to peak. Now some of you might be saying, well, if I screwed up v initial y the first time, I'm going to mess it up the second time. Possible. If you do that, and you swing on over to this equation, then you are not going to get the same answer for this one and this one. So you're not going to get the same answer for delta y if you mess it up for both. So what that means is that something is wrong, because ideally you should be able to get the same thing for both of these. Right now, something that is very good to do, and I wouldn't say totally foolproof, but it's, it's a good idea. Symmetry of projectiles is something that makes problem solving a lot easier. And what I mean by symmetry is that all things, if they start at the same level and finish at the same level, are symmetric around their highest point. So what we can do, even though this isn't necessarily how the object is moving, we can pretend that that is what it's doing and ignore the fact that it continues until it hits the ground or the water or whatever's going on. So we can ignore that and just focus on the symmetric piece, which means that whatever happens over here is the same exact thing that happens over here. So, how does that help us? It helps because in this equation, down here at the bottom, using the fact that symmetry is in existence, that means that our v initial y is our peak velocity, and our peak velocity is 0. So this goes away. So all we're left with then is delta y, peak to cliff, or cliff to peak, is equal to 1/2 gravity times time squared. And that time, because of symmetry, can be time up. So that makes that equation a lot easier to use than it was prior to that. Right? So that is all the stuff that you can do on the way up. It's pretty much that. Okay, so these are your equations. That's how you want to use them. The way down is not any harder, but it also is not any easier. So on the way down, let's see, that's going to be from all the way up here. Oh, darn it. Like that. Okay, so then this is the way up part that we already did stuff to, so we don't care about this. So we're starting right at the top there. Okay, so that means that our velocity at the peak here, which we said Vy is 0, this is going to be the initial of our downward interval. Okay, now at that point, from our previous diagram, we know this full height is going to be delta y peak to ground. Okay, what that tells you, not a ton of things, because not often are you given that value, but if you know the height of the cliff, which is to there, and you calculated the delta y cliff to peak, which is here, that means you know delta y peak to ground. Because the basic formula for that is delta y cliff plus delta y cliff to peak. So, for example, if you have a 5-meter high cliff and you go 20 meters above it, that means that your height above the ground is 25. Alright, so it's pretty straightforward in that whatever happens above the cliff gets added to the height of the cliff to get your maximum value. Now, when you know that delta y peak to ground, that means you can use a couple of the other equations because now you have another y value. So you can use this delta y peak to ground in this equation to calculate the time it takes to fall down. Now, this is the free fall equation, if you remember that. And it's free fall because it's just falling at this point. So delta y peak to ground is 1/2 gravity times time down squared. You can use that. And then you can use this time down here in this equation. V final y is equal to V initial y plus gravity times time. V initial y is the peak, which is 0. So that means that your V final y, which is how fast it hits the ground in the y direction only, is whatever your value for time is multiplied by gravity, because your V initial went away. Okay? Now if we zoom in very, very close to what the impact of a projectile looks like. Have your ground, and even if it appears like it's coming in totally straight, it's really not. It follows this little curve. And because it has this little bit of an angle, what happens is you have a couple components, everybody's favorite. You have a part that's pointing straight down, that should be a straight line, of V final in the y direction, and then you have a piece that's pushing it into the ground sideways, which is coming from here, which is V final in the x direction. So ultimately, what you have, I'm going to do it this way so you can see what's happening. Alright, we have a V final in the y direction, and we have a V final in the x direction, which gives us a hypotenuse of that, which is our absolute total V final. And how do you calculate that? By using the Pythagorean theorem. So you have V final is equal to the square root of V final x plus V final y squared. So that will give you your impact speed no matter the situation. And the shape of your object and your projectile is always going to be parabolic. So even if it's not a full parabola, it still has that shape. Okay, so this is how you do, or the formula is used for a height to ground with an angle. Okay, without an angle is much more simple. So with an angle, you have a lot of different variables, so you're going to have to do multiple calculations with delta y. Without an angle, however, things are so much better. So without an angle, we have totally flat. The object is launched completely sideways, which means your total velocity initial is going to be all x direction. So that means that your initial y velocity is 0. So you have your projectile, it gets shot out that way, goes down, hits the ground. Okay. Now, the cool thing about this is that this is just basically the same method of solving this projectile from this point. Okay, so you can pretend that there's like a cliff on this type of projectile, like that, and these two things are essentially the same. Now, why is that? Pretty much, it's because at this point, your y velocity is non-existent, and your y velocity is also non-existent at the peak of any other projectile. So, you have that situation going on here. Your VOY is equal to 0, which means your entire velocity is x. So when that happens, you know a couple things. We can use the free fall equation, which says delta y is equal to 1/2 gravity time squared, and that will give you the time it takes to fall. Now in this problem, we don't have a time up and a time down, we only have time down. So we just have one variable for t, and that is just plain old t. So we have delta y 1/2 gt squared. We can use that time and the x velocity. Sorry about the dog. So we use the formula of velocity is equal to delta x over t, and this is the only formula we have for x direction stuff. That's it. So once we get the time from this equation, we can plug it in down here, and we would have the velocity already, so all we're left with is delta x. So this type of projectile is much easier than the other one. And then we have our other type, which is a ground to ground. So that's just one level to the same exact level. So that is, it looks a little better drawn than that. It looks like that. It's launched from one side, it hits the ground on the same exact level. And the good thing about this type, this ground to ground, is that just like the other one, it is symmetric. So because it's symmetric, what that means is anything that happens on the left side happens on the right. So time up in this situation is equal to time down. So we don't even have to say that it's up and down, we can just say that it's time in the y direction. And because these two things are equal, the total time that it's moving in the x direction is double that value. So it's moving forward the whole time, half the time it's moving up, and then the other half the time it's moving down. Because of the symmetry also, the launch velocity is equal to the impact velocity, so you don't have to do any calculations. If it says that it gets launched at like 15 meters per second, it's going to hit the ground also at 15 meters per second. In this particular one, we only have one height value, so the only delta y that you calculate, I would say for the most part, is the maximum value for height. So you can use the same equations that we did before to get time. So you could say that v final is equal to v initial plus acceleration times time. In this case, v final y, v initial y, and then it's going to be time in the y direction, which once you have time in the y direction, you use the equation that says time x is 2 times time y. You can use the same equation for x as already mentioned. Velocity is delta x divided by tx to get how far away it is, which is the range. So your velocity is delta x over t. So once you get one particular calculation for this type, especially just the time y, that opens up a lot of different things that you can do. All right, so two quick examples. The first one, we are going to have a projectile, and I'm not going to tell you what type it is. So a rock is launched with a velocity of 15 meters per second at an angle of 20 degrees. That's all I'm telling you, okay? So velocity initial 15 meters per second, angle of 20 degrees. So based on that information, you have to establish what type of projectile it is. So is this a type 1, which is a height to ground with an angle? Is it a type 1 height to ground, no angle, or is this a type 2 ground to ground? So you can eliminate the no angle because clearly they have given you an angle. So then you're in between a ground to ground like this and a height to ground like this. Now since the problem does not specify an initial height, this is the one you're going to go with. If an initial height is not specified, that's what you got going on. Alright, so the first thing you want to do anytime you have a velocity total, which is a resultant, and an angle, you want to find the components. And in projectiles, these equations are always true. V initial x is equal to V initial times the cosine of your angle. So that's 15 multiplied by cosine of 20 to get your x velocity. And then the y velocity is V initial times the sine of your angle. So that's going to be 15 times the sine of 20. So we get an x of 14.09, and we get a y of 5.13. So those are your two velocities. Okay, now in terms of what we want to find, a couple questions could be, what is the time it takes to hit the ground? And the time it takes to hit the ground would be the time in the x direction, because it's going to leave the ground and then it's got to hit the ground again. So to find time in the x direction, we either need time y, or we need velocity in the x direction and distance in the x direction, because those are the only things that involve tx. So to get time y, if we look at that particular situation, we want time x. If we look for time y, what we need to know to get time y would be the v final in the y direction, the v initial in the y direction, and gravity. And if you look at that, at the very peak, velocity final in the y direction is always 0. V initial y we just found. Gravity, -10, and time. So we are going to get 5.13 divided by 10. So 0.513 seconds is time y. Okay, which means that time x is double that. So it is 1.026 seconds. Okay, so it is moving in the x direction for 1.026 seconds. Alright, so then the second thing you would want to figure out is how far is it traveling during this time. So the equation for that is velocity in the x direction, it's delta x over tx. Velocity in the x direction is 14.09. Delta x we don't know. Tx is 1.026. So delta x is then equal to 14.09 times 1.026. So that is 14.45 meters. So it lands 14.45 meters away. And the final thing that you could be asked to find is how fast is it moving when it hits the ground, or what's the impact speed. And because of symmetry, v initial and v final are the same, so that is going to be an answer of 15 meters per second. There's that. Okay. Other example, this is going to be a height to ground. So we have an object, again, same values, that has a v initial of 15 meters per second at an angle of 20 degrees. But instead of being launched from the ground, it is launched from an initial height of 16 meters. Launched from an initial height of 16 meters. Okay, so first thing you want to do, like the previous problem, is figure out VOX and VOY. And VOX is V initial multiplied by the cosine of theta, which is the same as the previous problem, so it's 1409. And then VOY is V initial sine theta. Again, same as the previous problem, so it's 5.13. Okay, so we want to find time up. And time up is from the cliff to the peak. So we're going to use V final y is equal to V initial y minus gravity time. So you can see plus gravity time or minus gravity time. Doesn't matter. The fact is gravity is going to be -10 and it's going to act opposite the motion of the object. So that's going to give us this relationship. 5.13 minus 10t, and that's time up. So time up is equal to 0.513 seconds. Okay, now for the entire time we're moving up, we're also increasing position. And we're increasing position, which is delta y. So the next thing that we would find with this knowledge is that delta y cliff to peak value. So like I said before, the symmetry says that we can go from peak to the level instead of from level to peak. So that means we can do 1/2 gravity time up squared. So that is going to be 1/2 times 10 times time up squared, which is 0.513 squared. So you get a value negative 1.32 meters, and that is the change in position. So it's going to go up 1.32 meters. Right? So we started at a height of 16, it's going to go up 1.32. So visually, got 16 over here, projectile, it's going to go up. We're going to do that. All right, so this is your 1.32 from there. All right, so next part would be to figure out how high it is above the ground. So how high is above the ground is delta y, peak to ground. And delta y peak to ground is when you take the change in height of the cliff and you add it to the change in cliff to peak. Now, if the height is 5, that means that the change is negative 5. So it's going to be negative 5 minus 1.32. But for this problem, I'm sorry about that, the change is 16, sorry. Got negative 16 minus 1.32, which means the change in peak to ground is negative 17.32. So the total height the object is above the ground is 17.32 meters. All right. Now that we know delta y peak to ground, we can use that information to figure out how much time it takes for the object to fall down. So delta y peak to ground, we use the same equation for the other delta y. It's 1/2 gravity time squared, but this time it's going to be time down. So we use negative 17.32. It's equal to 1/2 tan negative, and then time down squared. So we get 3.464 equal to time down squared. So then time down is equal to 1.86 seconds. Okay, so it's going to go up for 0.513 seconds and then fall down for 1.86 seconds. So how long is it in the air? What is the total time? So the time total is the sum of time up plus time down. And the total time it's in the air is also the time that it's moving forward. So time total and time x are the same. So time up was 0.513. Time down was 1.86. So when you add those two together, 513 plus 1.86, you get 2.373 as your time total, and that's the total time that's moving in the x direction. So it's moving forward the entire time for 2.373 seconds. So what do you do with that information? The final step, for the most part, usually is to figure out where it lands. Now we have one x equation, and that is that the velocity in the x direction is equal to delta x divided by tx. And velocity in the x direction we found way back in the beginning, 14.09. And that's equal to delta x, which is what we're looking for, divided by our total time of 2.373 seconds. So when we take that, we get that the delta x, or how far away it lands, is 33.44 meters. So it lands that far away. Okay. So that's how far away it is. We know how much time it's in the air. We know how much time it's falling. We know how much time it's rising. We know how high above the cliff it goes, and we know how high above the ground it is. So the last step here is to figure out exactly how fast it's moving when it hits the ground. So how do we do that? X velocity remains constant all the time, just as a rule. So V initial x is equal to V final x. So V initial equals V final, and that is going to be your 14.09. So those two things are equivalent. So the only thing left we have to do is find V final y. And we find V final y because it starts at 0 at the peak, falls down for the amount of time that it was falling, and then we end up with a final velocity in the y direction. So we do V final y is equal to V initial y gravity times time. So V final y is going to be 0 plus gravity, which is negative 10, multiplied by our time down, which was 1.86 seconds. So that 1.86 seconds goes here. So that gives us a final velocity of 18.6 meters per second down, which is negative. So we're moving forward 14.09 meters per second and down 18.6, which gives us an ultimate resultant velocity, which is your impact velocity, based on this formula. V final is equal to V final x squared plus V final y squared. So that's the square root of 14.09 squared plus 18.6 squared, and you can get rid of the negative because square of a negative is a positive number. So when you put this in to your calculator and get an answer, you're going to get that the impact speed, or how fast it hits the ground, is 23.33 meters per second. So it left the cliff going 15 and then hit the ground going 23.3, which makes sense because it has a lot more time to fall. Right? So it's going to take some more time to fall. Right? So if you'll notice, this little space over here is what happens when you have a type 2, which is ground to ground. And then this whole region at the bottom is what happens when you have a type 1 height to ground with an angle. So it takes a little more time to put these two together. All right, so there's a problem. There's a couple more notes up here. And that is, quite honestly, really all there is for projectiles besides more practice. So good luck with that. If you have more questions, just let me know.